So the last week example, I'm sure you can hear me properly. The last week example, we used to have a feedback loop, which GS was given and the HS was given, and the transfer function, of course, this one, and GS is equal 10 over S squared 2S 10, and the denominator of this one is S squared 2S plus 10 times 5 times, that's the one here, 5 times S plus 5 in denominator. So if you make that calculation, you are actually multiplying both sides with this one. So that is S squared plus 2S plus 10 plus 50 over S plus 5. Is that all right? So if you multiply with S plus 5, both sides of the denominator and numerator and denominator, so you multiply here, you can see that. But here, I probably the last week, I didn't forget that one. So you have to multiply this part with S plus 5 as well. When you do it, you are going to obtain the third degree in denominator, third degree. So it wasn't the second degree as I mentioned here. I'm sorry that probably my microphone and also my camera was closed, so I start from very beginning. Last week we it was a problem that is the feedback system, and we were going to obtain the transfer function of it. You remember that this one is the GS and that one is the HS. So GS over 1 plus GSHS is our transfer function of this feedback loop. And if you write down here, so that so far is correct. So far it's correct. That's correct. However, if I multiply with S plus 5, I've forgotten to multiply this one. So that is wrong. That is wrong. Okay. Now the correct one here is this. That's the correct one. So when you reach to this one, but I wish you could have done that calculation and you say that I made a mistake. You see. So if I multiply both sides with S plus 5 here, so if you look at that transfer function, multiply with S plus 5 here, then I have to multiply with S plus 5 here too, but I've forgotten last week. So if I did it here, then you are going to obtain the denominator is going to be the third degree differential equation. So we have, I don't know whether you can see that. Yes, you can. So we have in denominator of the transfer function, this is our transfer function. Denominator of the transfer function, that is we have three roots for the denominator equation. Okay, and also 1 0. S minus 5 is 0, but we have to calculate that one. Okay, that's the correction I made. One thing I should mention is also important, which is called sensitivity. I don't know why this happened. So I have a question now. Have you seen this correction? I don't know when our communication stopped. Therefore, I'm just asking you, have you seen my or have you heard my explanation about this one? Yes, okay. Thank you very much. Thank you, Mohammed. All right. Now the other topic important is sensitivity. Now, what's going to happen here? You have a feedback system. You have a simple feedback system, let's assume. Tell me if you cannot see. Sometimes the vision goes out of my, my pencil becomes out of the system. We have a G here, okay? That one is RS, input, plus. And that one is, let's say, YS, output. And that one is our feedback, unity feedback system. And this one is minus, okay? Transfer function is equal to TF is equal to G over 1 plus GH. There's no H here, so 1 plus G. Okay, this is your transfer function. Now, sensitivity is the definition of sensitivity. With parameter change of G, how much your system's transfer function is changing. In other words, delta transfer function over transfer function that represent the change. If you don't understand, just say stop, and I start from very beginning. What is that one here? That is the change of the transfer function with respect to transfer function over delta G over G. So how much change occurs in percentage is how much change occurs in transfer function here. So then if you, that is percentage in TF over percentage change in G. That is what sensitivity is all about. Okay. So that is delta TF is incremental change of TF, transfer function. For this simple system, by the way, S TF over G is equal to delta TF over delta G times G over TF. TF is in the denominator. You remember that. This one is denominator. So that is the same equation. So if you write this one, you are going to obtain that tek tek yapalım. G over G, I'm going to make it G over TF is equal to G over 1, sorry, G over 1 plus G, which is equal to 1 plus G, okay. Delta TF over delta G is equal D dG bracket G over 1 plus G, which is equal to, first get the 1 plus G, 1 plus G minus G over 1 plus G square. Do you agree with me? I just get the derivative of this one. The derivative of this one multiply with this one minus derivative of that one with multiply with that one. So that is equal to 1 over 1 plus G square. Okay. So if that one is here and that one is there, so I continue here. I just okay, there's no message. Computer itself is giving me signal. 1 plus G, that one is 1. First one, this one, 1 plus G square. So this one is equal to this. So that one. This one is equal 1 plus G. Result is equal to 1 plus G. So I don't know whether you can see my finger. No, you can't. If today I'm only today I'm experiencing that. So I'm just going to start from very beginning. This is the I don't know what's happening actually. Can you see that? I'm time to time I'm going to look at my computer and whether we are losing contact or not. Now, the I just want to complete this part. Sensitivity is something by changing percentage change in the gain of the system, what your transfer function is affected that. So percentage change in transfer function divided by percentage change in G. So that if you divide that one here, so you make some simplifications here, you are going to obtain this one. In order to find that one, you can calculate that one separately. You can calculate this derivation separately. This is easy. If you divide G over TF, you are going to obtain 1 plus G. However, if you get this derivation, then you are going to obtain uh, the the derivative of this one with multiply 1 plus G, and the derivative of this one with multiply with this one, the second term. So it becomes 1 over 1 plus G square. So if you write 1 plus G square here times 1 plus G, then you are going to obtain this one. If you have, instead of this feedback loop, if you have I think I have to leave that part. However, you already know that sensitivity of a transfer of the system is equal 1 over 1 plus GH. That means a feedback loop is actually reducing the sensitivity. Sensitivity is something that your system transfer function is changing with. You see, in order to understand the sensitivity, you have to think about the monetary system, the economical system. If you say that, for example, or not saying that, if you change some parameters in your monetary system, then the output of the system, for example, the Turkish lira, dollar versus Turkish lira. If you take some good measures, then sensitivity goes down. If you take some for feedback loop, it is good. Feedback loop reduce the sensitivity. Sensitivity is a risky for control systems. I think you understand now what sensitivity is all about. Let's come back to our original course material. It's going to be very fast. All last week's. So we are warming up. That is a rotating system. That's a rotating system. The mass, friction, and the torque load is affecting, and it's a theta position control. Last week we discussed that one. This is a linear motion, mass, friction coefficient, and also viscosity. Elasticity is important here. For that equation, you might take elasticity into account as well. That's the repetition of last week material. What we have already seen, these are simple. Feedback loop, we have already obtained the feedback transfer function of this feedback loop, but the output is equal input times transfer function. Don't forget that one. Last week we did that. And also we solved that problem. So I said I made a mistake last week, so I made correction. You remember that? And these are the simplifications. This is the product. Multiply these. This is addition, sum, and that one is feedback. Okay. This is multi-loop system. That was important. Remember that part is a controller part you are going to design. It was, remember, on-off controller. We have talked a lot about it last week. However, if you look at this is the actual control problem. The proportionality constant, this one Kp, it's good that you increase the Kp. So you are actually amplifying the error, then your control system aware of the fact that what is going to change it, all right? So this is proportionality constant, Kp. That one is integral control action. So if you have error, then you are actually get the cumulative error in order to make correction, and the transfer function is 1 over s. Remember, of course, there is a integral gain here, adjustable. It is you are going to decide the value of those, and that is PI controller. P, that one proportional, I integral. And of course, transfer function of this one is this. If you get the derivative of the error, in that case, şimdi bu error habire söyleyip duruyorum. Şuradan bakalım. Bakın bu your controller. The error signal is coming, and this is the output signal of the controller. So you multiply for this example. You get integral for this example, and then you multiply with proportionality constant and get the integral value, and then this one you get the, of course, proportionality constant plus you have derivative. You are now getting the errors. Derivation of the error, derivation of the error is telling you the future, actually, what kind of change is occurring. You can see that from that point. We are going to discuss. But don't forget, these are the transfer function of those. And finally, most popular controller is called PID, proportional, integral, and derivative all together. And when you derive those, last week we did it, you obtain that kind of additional. You see, the system is in this part. This is a controller you are designing. So what we are obtaining, we are actually adding. There are two s here. The roots of the numerator has got two s's. So therefore, you are adding two zeros, two zeros to the system, and one pole to the. We are adding it. Okay. That is what PID is all about. And if you have multiple inputs, we already know that if system is linear, then we can actually employ the superposition theorem. Therefore, we can neglect one of them and solve for the other one, and then neglect, for example, for this case, neglect first ds and obtain the output for rs. Then you neglect rs and obtain the output for ds. Okay, then get the summation of those. This is what superposition theorem is all about. You remember that. That is what we have done. You obtain the main input transfer function, you obtain the disturbance input transfer function, and according, if you know the transfer functions, you can calculate the outputs. Output means transfer function times input. Okay. And of course, this is easy. We've done that. That is what we have solved. You remember that RC network. For RC network, you can write down or represent the system with block diagrams like this. EI, that is the input, and EO is the output. So that's the relationship. You can see that. That is what we have done. State space, I'm not touching yet. Okay. So that was the end of the last week's course material. So we just warm up in 10 minutes. Then we come back to today's material. Of course, additionally, we have seen the sensitivity problem. Sensitivity is a mathematical description of the systems, how sensitive that's those systems with respect to parameter changes. Now we are going to concentrate on the systems. Today we are going to more concentrate on the systems. Now, if you have a spring like this, let's actually think about this. You have a spring, and also mass here. All right. So forget about the mass for the time being. So this one is the, I'm sorry, follow my cursor, please. This one is the example. You are actually giving a torque. You are actually giving a torque, and then your system is rotating with that torque. But this is input part of the spring. That is output part of the spring. Say torque is directly transferred to the output. So input torque is equal to the output torque for spring action. But speed is changing. This speed is not equal to that one. There is a change in the speed. That I brought that pictures not from Ogata's book. This is Bishop and Hoft's book. I believe it handles the matter more comprehensively. The Bishop's and Hoft's book is considering that some values are through the torsional element, through the variable. True variable, torque. Torque is equal. However, a cross variable is speed. Now, this is the general representation of this one. For electrical one, current flows in, so it's a true element. But charge, you know the famous equation. I is equal, ben pedimi kurayım bir dakika. Just a moment, please. So you can see that current flows in a system, but current means dq dt. Therefore, Q is equal integral I dt. So integrated true variable. This is a true variable. İçinden geçen in Turkish. Variable across element. O da uçlar arasındaki. I'm sorry for Turkish. That is it's not clearly defined in English. The terminal voltage between terminal is actual across element voltage difference V 2 to 1, and that is the flux linkage. Of course you know the relationship with flux. Bunu yazmaya çalışayım bakayım şuraya köşeye. V21 is equal to Faraday law. Voltage is equal flux linkage here, flux linkage over dt. Derivation of it. So these are the relationships. Similar relationship is obtained for force and torque. For force, m times double x double dot. That means m d square dt over dt square x double dot is equal to m dv dt. And momentum here, you remember momentum, we are not going to use quite often. However, you have to understand that one. These are mechanical quantities. mv. And torque here is J times theta double dot, which is equal J. Buraya da bir şey yazalım. Şuraya yazayım onu da. Ya da aşağıda da yer var. D theta dt is equal omega mechanical, theta mechanical. Okay, so that's why J double theta double dot square derivative is equal J. This is the first derivation of the speed. Angular momentum is equal J times omega. That one, momentum is equal here, m times. M is mass. Of course, speed is equal to V is equal to dx dt, derivative of the x. You know those systems. That one, the early one, was equal to across variables, current, force, torque, and in also the fluid and thermal. If it is necessary, you can learn the fluid and thermal. For electric people, I don't think it is very important for you. Anyway, but if you need it, you can look at it here. Okay, these are true and across variables. However, that is summary of the governing differential equations for ideal elements. Ideal elements. Ideal means there is no loss in it. Inductance, for example, or spring, or biraz büyüteyim, ben de göremiyorum. Rotational spring. This is a translational spring, and that is, this one is inductance. That is translational spring. That is rotational spring. And also this one is fluid inertia, they call it. So LdI dt is a very famous equation, and the energy here 1 over 2 Li square. I don't agree with that. Also right here, power, they say. This is energy, actually, stored energy, 1 over 2 Li square. If it is a capacitance, what are you going to do? Who's going to tell me what's the stored energy in your capacitance? You have already passed the circuit theory. 1 over CV square for capacitor. 1 over 2 CV. This is Li square. The other one is CV square. V is the voltage and C is the capacitance. Anyway, so these are ideal elements. There is no loss involved. However, the other ideal elements, so I continue, the capacitance, for example, 1 over 2 CV, biraz büyüterek göstereceğim, 1 over 2 CV square, and the representation is C. Mass is also ideal system, no loss involves, just store energy, mass. That's why you cannot accelerate, for example, mass of the track is much higher, and or there are two vehicles. One of them is a sport car, which is light. The other one is normal car, which is heavy. If you give same torque to wheels, the sport car is going to accelerate faster than this, since the stored energy requirement is less. That means you are actually, while your vehicle is moving or accelerating, you are actually storing energy in it. You store mechanical energy in it. Anyway, so if you come back here, mass is also another translational element. The energy is equal 1 over 2 mv square. It's a stored energy. For rotational mass, torque is equal J d omega dt, and energy is equal 1 over J omega 2. Sorry, omega square. Omega is a mechanical, by the way. Fluid, I'm omitting those equations, fluid and thermal. You might need in the future thermal equations. If you involve the power electronic system design, then the cooling of the semiconductors might be important for you as well. Not control at the moment. Resistance, however, is completely different. It's not ideal element. I add here, but this is, look, energy dissipation. Electric resistance is R. So current is equal voltage over R. Power is equal voltage square over R. Or Ri square. Ben Ri square'i daha çok severim. Bunu da yazı vereyim şuraya. Ri square. Since you can see that you have the current here, eşittir. And also translational damper. That B is a viscous friction. So power is equal B times V square. Force is equal B times V for translational motion. V is the speed here. V is speed here. For rotational, however, omega is also speed, radian per second. V is meter per second. Omega sorry. Omega mechanical radian per second. If someone says 1 over S, that's correct. Radian hasn't got any unit. Birimi yok radyanın. So translational damper, which that means loss, by the way. That is loss. Kırmızıyla gösterelim bunları. Bunların hepsi loss. Bunlar so you cannot get it. Heat olarak it converted to heat and dissipates. Rotational damper as well. Loss. Fluid system, you also have loss. Of course, the viscosity is proportional with the resistance. Thermal resistance is also important. How could you transfer the energy, dissipate the energy for thermal system? You might use those ones. You cannot get those energy back either. This is a easy problem. You have a mass, you have a spring, and this is a spring mass damper system. You know that the definition of that kind of system is a free body diagram. Free body diagram. Free body diagram is this. This one is free body diagram. What is saying that? Let's look at together. What's saying that? System, because of the mass, system has got a force going down, or you are actually pulling it. You are actually pulling it. This is an additional force. Okay, so you apply a force here. I repeat, it's not the weight of this one. It's you apply a force here. This force, there is a resistance. What's resisting? The system is in equilibrium case. Without the force exertion, without the force giving, system is in equilibrium, dengede. So you are actually, can you see me, by the way? You can't see me. Şu kamerayı değiştireyim. You can't see me. Now I think you can see me. So this spring system, we are actually pulling it with the force F. Since system was originally in balance condition, equilibrium condition, balanced, then some forces are going to be against my force. One of the force is a spring. The other one is friction here. So the equation is going to be this. M, y here representing the position, by the way, similar to x. Y, m d square y dt square plus friction times dy dt plus k times, this is viscosity, yt, is equal force in time domain. But if you write in speed, if dy dt is equal v, then you can write mdv dt plus bv times k integral v dt is equal to force. You can also write this equation as well. What about that one? You know the circuit theory. However, I'm going to help you a little bit, or make it, not helping you, make it a bit simpler for you. IR IL IC. So that one, the first term is V over R, is obvious. C dV dt is the current of the capacitor, IC, and that one, that is IC, and that one is IL. Since V is equal V, there's a current source, by the way. So in V is equal LdI dt. So I is equal integral V dt. Okay. So this is the differential equation for the electrical system. However, if you come to the mechanical system, if you come to this mechanical system, mdv dt plus bvt k times v dt, tekrar yazıyorum, I repeat this, m times dv dt plus b times vt plus b times vt and plus k times integral is equal force. Look at the similarities. So mechanical systems have their electrical counterparts. Quite often we solve those equations as if sanki they are electrical. We solve those equations. When you solve those kind of equations, of course, this is for example one parallel RLC network. That is the voltage. By the way, this is the voltage. Geri dönüyorum. Come back. So that is the voltage here. You define the voltage. That is define the voltage here, V. sorry. Voltage here. So voltage divided R. And also you can, when you solve it, you obtain, this is a of course second order differential equation. You are getting the derivative of the current as well, and then you solve it. We are going to solve those equations, by the way, don't worry. But the response is going to be something like this: a sinusoidal function and diminishing, and then becoming zero. So voltage is becoming zero at the end. This current is not continuous, by the way. Otherwise, you cannot get the zero solution. This is the impulse type current. Linearity. I think we deserve the break. We are going to take a break. Now it is 10 o'clock. 10:15. 15 dakika veriyorum. Biraz we are going to, ya da 10:14 olsun. Tamam mı? 10:14. 10:15'de başlarız. Take a break. Okay. Evet. Now we are going to start again. This this system, any systems in the physical life, has got a function like this. A function like this. This function is equal y f equal y squared. This function is not linear, by the way. It's not. So what's happening here? We have to linearize that one. What are we going to do in order to linearize this system? We are selecting a point which is most likely to represent the case, and linearize the system and change it as if it's a line. Okay, so this linearization process is called that is the equilibrium point, operating point. For that case, we have this is a function, by the way, and the function function with respect to y, changing with respect to y. So f is equal y square. You can see that. And also we are going to obtain df dy at equilibrium point with respect to. So I'm going to write down the linear approximation here. So you let me know. I hope we don't lose the contact. Okay, there is something wrong. I don't know whether are you, probably it's at 10 o'clock, something like this. Is the system, Blackboard system is heavily used. That might be the reason. So immediately send me a message as long as we lose the contact point. I think you can see. You can see my hand. Şuradan başlayacağım. Bir dakika. Yes, you can see my hand. Now, just assume that y is equal function x, nonlinear. Y is equal fx is a function, and the operating point,
Excuse me, Professor. I'm sorry to
yes,
interrupt, but on, on the recordings, only the main slides. We can only see the main slides. Your camera isn't visible on the recording, so we can't go through the questions when we study. So, is there any other way we could solve the questions?
I don't know. I've been thinking you can also uh, following my recorder as well. You couldn't be able to see it when you open it up,
No, we cannot see the front camera recording. We can only see the slides and the voice.
but you are seeing the slides. Assume that I was in the classroom and I was writing on the blackboard. You were not recording it, by the way. Similar, isn't it? You
Yeah,
understand what I mean?
yeah.
Okay, so but I'll try to find a way for this. Okay, now the operating point, you just write y is equal to, it's a Taylor expansion we employ. I'm sorry. Get the first derivative of the function with respect to s, x minus x operating point plus 2 factorial. You know the Taylor expansion, delta square f over delta x minus x squared, so on. So the value we are going to evaluate for those, and we assume that the system higher derivatives could be neglected. In that case, y becomes, I repeat, if you neglect the higher order terms, this is Taylor, by the way. Taylor, yes. Bir dakika, bir şey yazdı birisi, okuyacağım. Well, Ahmet, it's a difficult question to answer it, so we can discuss it later. It's not the content of our course now. I don't want to interrupt the course. You can send me an email if you want. So this k here, why that is equal fx dot, and k is equal the first derivation. Then the final equation becomes y minus y dot, sorry, y k x minus x prime. So that is the equation we derive, okay, and linearize this system. So this is the linearized case of the function with respect to the system. So that probably now you can employ the equation is equal function, for example, y square. You might call it x square as well, and then you can solve it and make it linear at this point. Is it clear right now? Shall I repeat that one? This, you expand this function with respect to, you can follow my pencil please, with respect to Taylor expansion. We neglect the higher order terms, so we use this part, and then your system becomes a relationship between y and x is become a line. Although if you ask me, it is still not a proper linear since it's not crossing zero. However, it's called in literature, it's called linearization. I just review the S-domain equations we widely use. You remember that, so I'm going to be a bit fast on this one. For step function, it's 1 over s. For exponential function, it's 1 over s plus alpha, that one. For sinusoidal omega, for cosine is s in numerator. Otherwise, denominator is the same, s squared plus omega squared. So t over n is equal n factorial s over n plus 1. And the function, derivative of the function, derivation, we have already reviewed that one. You remember I put Professor Nick's book or notes about Laplace conversion and the functions, and you can see that for the second derivation, you have to multiply with s, which initial value. For the third equation, you have to multiply with the derivation of the function, and then put other initial values as well. You know that. You are not going to use third or fourth order systems in my course. And also, if we continue on this manner, integral means is 1 over s, by the way. If it is you see definite integral, you can see that this one as well. Impulse function is 1, you remember that. These are exponential function times sine omega t. That's the exponential times cosine omega t. That these are here. And also the other some complex equations are already given here. That one we are going to use, by the way. Kalem koyayım şuraya. That one we are going to use. This is a typical second order system transfer function. Now I would like to concentrate on electric machines. Okay. For electric machines, by the way, that model is still used in books. However, I don't like it, that one, this model. Since that one is cancelled, the field excitation is cancelled. Instead, permanent magnets are replaced. So it's the permanent magnet driven DC motors, which are widely used, are called brushless DC motor. So that conventional representation is illustrative. So you can see that the electric motor itself, for example, produce torque. However, there is a friction. Friction is represented with bearings. So those bearings are assumed to be a constant viscosity value. And also, this is a mechanical structure. You always have an electrical equations as well. So I'm going to I understand your criticism. So I'm going to continue this one, but I'm going to write down every equations here instead of paper. I'm going to write here. Okay. So in new DC motors, there is no field current and no brush and commutator. Field is provided by permanent magnets. Try to develop permanent magnet DC machine transfer equation. All right. So I'm going to do it. So I'm going to open up a clean white page. Electric machine. Transfer function. Okay. Electric machine is something like this. This is the model of the electric machine. That is L, that is R, and that is E. And the current is going to flow. Current is going to flow. So the differential equation here is L di dt plus Ri plus E is equal to, buraya da V diyelim, V. V is a DC voltage. It's equal to V. For steady state, however, V minus E over R is equal to I. For permanent magnet, by the way, for permanent magnet machine, permanent magnet, machine, torque mechanical produced by system, torque mechanical is equal to K times I. Buna K torque diyelim. Torque constant times I. In S domain, K times IS. So torque S is equal in S domain. I converted time domain equation to S domain is equal to this one. This current, let's assume that this current is IA, okay? So it's IA here. And E, the E voltage source, şuraya yazayım. E is equal to, for normal machine, for permanent magnet, K times omega mechanical. So K is a design factor, by the way. So those equations are valid. Therefore, if you write this equation in time domain, sorry, converted to S domain, L times S IS plus R IS, sorry, plus ES is equal to VS. So one equation is simple here. IS times SL plus R is equal to VS minus ES. E here is the inner voltage, by the way. Inner voltage of the, or sometimes people call it back EMF. Probably now you are taking electromechanical energy conversion. Therefore, you are learning the basics of electric machines. This is one equation. So electrical equation, tamam mı bu? Şimdi bir de mechanical equation yazacağım. You have a mechanical system connected to this. Onu da bağlayayım şuraya. Başka bir renkle bağlayacağım. Mechanical'ı. Mechanical siyah olsun ya. You have inertia. You have B. Şu o kadar lazım değil bize. Şu o kadar lazım değil. Nasıl olsa yazdık denklemini. We already derived the equation here. C bunu da güzel yapalım bari. Madem öyle mekanik kapı siyah dedik. It's going to be red one. This is our mechanical gate. Saçma. İstediğim gibi çizemedim, bir dakika. This one is systems inertia, J, and also this is friction represented like this, and also we have, let's say, load. So this is the mechanical gate, okay, the load. So I'm just writing the mechanical equation here. J d omega mechanical dt plus b omega mechanical is equal to, we are neglecting the friction, is equal to pardon, bir şey daha unuttum. Ne var karşı koyan başka? Şuraya yazayım. Torque load. Çocuklar bu load'u ben hiç beğenmedim. Bir dakika. Kalsın istemem böyle. Hoppa. Bu da load. Diğeri de torque load. Okay. Şimdi buraya we are going to add that one here. Plus torque load is equal to torque mechanical. Torque actually electromechanical. That one is also torque electromechanical. So if you write this equation again here, the second equation here, now omega s bracket Sm plus V is equal to torque electromechanical minus torque load. Of course, these are S. If you look at the similarities between these two equations, you can see that one equation here, current is equal Vs minus Es, and here speed, current is equal Vs minus Es over SL plus R, and omega S is equal T electromechanical minus TLS over SM plus B. If you agree with this one, so we can come back to our original figure, but don't forget those. So in order to find the current, we are going to compare the V minus E over SL plus R. You are going to obtain the current. Now, if you look at the feedback loop, you are going to see the same result here. I go back. Bu resmi kullanmayacağız. We are not going to use this figure since we haven't got field control here, so we are not going to use it. Okay. Bunu hiçbir zaman kullanmayın. That's the one which is clear enough. Now voltage supply, input voltage with the speed times K is giving you the E. That is E, by the way. Onu yazayım buraya. Kırmızıyla yazmak istiyorum. Karışmasın öbürleriyle. That one E. So V minus E times 1 over Ls square times K, you obtain the torque. Are you with me? Are you with me? Evet, tamam. Yani with me'den kastım, I mean, are you following me? So this torque is produced by electric machine. If you take torque minus torque load, which they use torque D here, this is a difference. I'm not going to use this one. Torque load is a different material. So the difference between those, multiply with, oh, I said man, M. I'm sorry. I have to come back and replace my equation here. But concentrate on this one. I'm going to explain this one again. That's right. So you can see that there's a J here. So I get rid of it. For translational system, by the way, mass is correct. It's not wrong. However, it's rotational system. I just write J here. S times J S times J plus B is equal torque electromechanical minus torque load. So if you come to this figure again, you can see that we are going to obtain the omega here. Omega is equal to the torque difference divided by this one. And also here you can see that current is equal to Vs minus Es over SL plus R. So if you multiply current with K, then you are going to obtain the torque. Tekrar gidiyorum. Now, V minus E times 1 over R plus Ls is equal current. Current times K is equal torque. So if you find the torque here, you can see that torque electromechanical minus torque load, this is torque load, is equal, and multiply with this one, you obtain the speed. If you get the speed from here, multiply with the constant, then you obtain the voltage, inner voltage, E. So that is the block diagram, which is equal to what I derived equations like this. Why do we multiply with 1 over S here? What are we doing with multiplying with 1 over S? Kim yazacak? Merak ediyorum. Who is going to write? Why we multiply with 1 over S? Nobody is written. Interesting. Sorry. If you integrate a function, which is this is a definite integration. Indefinite integration, you have to multiply with 1 over S. You can see that 1 over S. That means we are actually in in S domain, we are actually integrating the speed. If d theta dt is equal omega mechanical, then theta is equal integral omega m dt. So we are actually integrating it. In S domain, when you integrate, multiply with 1 over s, you are integrating it and you obtain the position omega. Okay, so this is a typical servo control system. It's called servo control system. Robot arms and things like this. One side is electrical part, the other side is a mechanical part. For brushless DC motor, by the way, o denklemi bir daha yazacağım kırmızı olarak. For brushless DC motor, generally speaking, torque electromechanical is equal K times I, and E is equal to K times omega mechanical. So these are approximately equal, those K values. So we have, you can see that two Ks here. One of them is KV. That one is KV. Hello. That one is KV here. That one is KM here. İsterseniz öyle yazayım, daha kolay olur sizin için. KM. That one is KM. That one is KV. Hem görünmüyor tabii. Sorry. Puntayı biraz düşürüyorum. Yeah, okay. Km times I. So you multiply with Km here. First we obtain current, then multiply with Km, we obtain torque mechanical here. I call it torque electromechanical, by the way. And we compare it with the load torque. Then we multiply with this one. We obtain the speed. Of course, speed is multiplied with kV here, the voltage kV here, and then you obtain the E here, inner voltage of the brushless DC motor, and V minus E is going to give you if you multiply with this one, you obtain the current. Then multiply with K, you obtain the torque. Okay. And integrating, if you calculate omega, integrating with omega, that means 1 over S, you obtain theta. This is a typical position control system. This is a fractional horsepower DC motor values. So you might get an idea about what's all about. I just have got news from Energy Portal. Can you see my Energy Portal, by the way? You cannot see probably. They say Toyota is going to produce charger plug-in. It's called plug-in. So hybrid electric motors, which has got plug-in facility. Toyota, I'm very much interested in electric vehicle business. Probably you know that. And Toyota is one of the, let's say, safest investment they do. They have good hybrid vehicles. Now, plug-in, of course, is going to means that the range is going to electric driving range is going to increase. It's a good technology, plug-in hybrid. Okay, let's go. Now, this is, I'm not sure whether it is directly linked with my course or not, but generally speaking, the operational amplifiers are used for control systems in analog networks I'm talking about. For, of course, you have learned, by the way, have you got any idea about what operational amplifiers are all about? Right? Yes veya no diye yazın. Evet, görmüşsünüz. Şimdi, the thing is this. That one is output, this one is input. But this amplification, this actually comparison device, there is a resistance and there is a parallel, not parallel, input-output connected capacitors. If you have a network like this, your output is equal to minus one RCS. Transfer function of this one is equal minus 1 over RCS. Integrating, it's called integrating circuit. Neden integrated diyorlar? Why they call it integrated? Since 1 over S involves. 1 over S is an integrating element. Okay. Şimdi başkaları da var. Differentiating circuit. In that case, you multiply with S. Okay. What's the difference, the other one? For the early one, C was here and R was there. When you replace those, if you put R here and C over there, you get minus RCS. These are also inverting, by the way. Inverting means getting opposite polarity. Okay, minus one CR. And if you look at the differentiating circuit, not exactly equal to this one, but if you add another one here, R and C parallel here, then you obtain this. We are not going to derive those equations, by the way. It's not our job. But what we are going to learn, what we are going to understand, we are going to have different transfer functions. So if you want to manufacture or if you want to design a integral controller, you are going to use the integral action. If you need a differential controller, you are going to use one that is integrating filter. They call it filter. However, it's a controller actually. For if you're adding another capacitor here, then you obtain this transfer function. So the transfer function output input relationship is a function of the parameters C1, R1, RC divided by C divided by S, by the way. S is important here. Okay, this is integral action. So these are now. This is summary, by the way. I picked those figures from Bishop and Holt's book. That is DC motor. Don't use that one. There is no such thing now. The field current control, probably some old motors, field current control. Armature controlled. Armature controlled means voltage control, transfer function of it. And also AC machine transfer function is given. That one is important. Bakayım kaç tane kaldı? Ha, biraz daha var. That one is important. Gear is widely used in control systems. For example, in electric vehicle, our electric motor speed is more than 10,000. However, the shaft which connected to differential has got 1,000. So 1 to 10 ratio occurs here. For those, by the way, for gear system like this, the gear ratio is M1 over M2, which also represent the R1, the resistance over R2. But neglecting the loss here, input power is equal to the output power. Neglecting the loss. Power neye eşit? Ya yazalım bir iki denklem, birazcık şey yapalım. Power, ne oldu bu? I'm sorry. Anormal büyümüş. Power is equal torque times omega mechanical. General equation. So power 1 is equal torque 1 times omega 1, and power 2 buraya yazacağım. Eşittir torque 2 times omega 2 which is equal to power 2. Of course, approximately. When you neglect the losses, input power is equal to output power. Buradan şu sonuç çıkıyor ki çocuklar, that is the result we obtain. T1 over T2 is equal to omega 2 over omega 1. Bu denklemleri bilmeniz lazım. Gear system. You are going to face with a lot of gear systems, and you are electrical and mechatronic students. Probably you don't have enough knowledge about the machines, and you can see that the N is also represented here. So the gear system is also represented here, shown here as well. So, but this one is the one you should not forget. If you increase since power is the same, if you rotate it in a fast, that means speed is high, for example, for electric motor. Speed of electric motor is good, is high. That means torque is low. If torque is low for the power, if you increase the speed, follow me. If you increase the speed here, then the torque goes down for the same power. Then you are going to, less torque means less current. Less current means less conductor, so it makes the electric machine smaller. That's why electric machines run, for electric vehicles, run over 10,000 RPM. Anyway, this is the equation. So this gear also might be used as a torque amplifier. Since this one is operating with a lower speed, assume that this one is as a lower speed. So if speed is lower, then of course torque is higher. Okay. Speed reduction or torque reduction or torque amplification, what gear system is all about. Of course, he described as theta. Theta is position. And also neyse daha fazla girmeyeyim. That is potential voltage divider. This is also still used. So the position of theta is a function of the R. So R2 is the R1 and R2 are the total resistance is R. However, R1 is the one which is connected. R2 is R2 is the one connected to the load. So the ratio is proportional with this one. So you can fix the resistance values in order to change the voltage as well. This is also another representation. So for the battery, for example, you can get one terminal from this part, you can get another terminal from that part, and you can see that the output voltage is equal to theta 1 S over theta 2S. So it's a rotating system. Anyway, these are voltage dividers. Bu ne bu? Biraz büyüteyim. Tachometer. As I told you, when you measure the speed, you generally use tachometer. It's called velocity sensor, or it's kind of generator. So voltage here is proportional with speed. You can see that. So voltage here is proportional with speed. DC amplifier. DC amplifier, it has got this relationship. Output divided by input has got this relationship. Ka over St plus 1. Tau is the time constant, is R times C. Evet, bu da şey. These are reference for you, by the way. Accelerometer. Operation principles of the accelerometer is this. So you have a system in it, and there are wheels here, and the speed of the Y and the speed of the X, the frame speed is this one, and the relationship is equal to XO over XM. I'm sorry, X input, this one, X input over XO. I'm sorry. If you need it, the transfer function of this one is equal to this. Okay. So there are double zero here, S0, and there are two poles, and function of B and M. B is a friction coefficient and M is the mass. Of course, K is also represented here. Bu da önemli çocuklar. Thermal heating system. That's, I don't know whether you need it, but C is the thermal capacitance, Q is the flow rate, constant. Q nedir? Flow çocuklar. Yani metreküp, 1 metreküp saniyede geçen akış sayısıdır. The flow is the one in 1 second, meter power to 3 meter flowing the liquid or thermal system. So this is input, that is output, and the relationship is equal to temperature. This one is the temperature difference due to thermal process. Q is the transfer of rate of heat flow of heating element. Lazım olursa bakarsınız. Bu önemli ama bakın. Bu önemli. Bu nerede kullanılıyor biliyor musunuz? Bakın nerede kullanılıyor. Şu direksiyon. Şu direksiyon bili. Burada bir yardımcı motor var. Direksiyon biline yardım ediyor. Ama sonuçta burada bir dişli var. Bu tekerleğe bağlı. Arabanın lastik tekerleği. The wheel of the vehicle. Bu da buna bağlı. Şöyle tam ortaya değil ha. Not center of it. It's connected. Therefore, there is a gear here. This one is rotating. This is wheel, steering wheel. This is steering wheel. And that one, these are actual wheels of the vehicle. And that one is rack and pinion mechanism. Rack and pinion mechanism is here, is used, widely used. Equation is obvious. X is the linear motion, is equal r theta. R is the radius of this wheel, okay? Başka ne var? Bunu yaptık. We have already solved that one. You remember that? We transfer this one from here to this one. Remember that. Ne yapmıştık? Divided by G2. G2'ye bölmüştük. Evet, devam edelim. Yapılan iş burada belli. Bunu yaptık daha. We have already done that. This is also another example. Remember that the disk drive system. You remember that. This is the arm. An electric motor is connected here to rotate the theta control. These are the equations of the disk drive system. DC motor here, okay. Bir dakika. That is DC motor here, and that is amplifier. That means controller you are going to design, and the actual head position is compared with the required desired head position, and the error is this one. This is your system, okay. So if you look at that one, you remember we have already derived the electric machine equations. So this is the simplified version. S times GS plus B LS plus R is the representation of the electric motor, and position. Nereden çıktı demeyin. Don't say that we don't know this. We already know that. You know that. Bir S ile çarpıyorsun. Bir bu var. Disturbance'ı bırak şimdi. Forget about that one. That's this term plus this term plus 1 over S. You multiply those. Yürüyorum. That's right. That's the one. And this is the differential, well, the block diagram modeling of it. You can see that is electric motor parts, including the mechanical structure, J inertia, and these are the electric machines values. This one is a sensor, and that's proportional controller we use. Typical parameters for data, disk drive reader data is this. Unity, is it a correct unit? J is Newton meters second square. Is it funny, isn't it? Acayip mi? Ne dersiniz? No, it is not. Biz hep kilogram meter alıştık. We get used to kilogram meter square. However, since the torque is equal to so this term, theta, is equal radian per second. So the second derivative is equal S square. Therefore, the torque is Newton meter. Newton meter. So that's correct. Friction is a Newton meter second. And also these are the constant values. When you solve this differential equation, when you solve it, so this is the system. Just for proportionality constant Kf40, obtain transfer function Tf Ys Rs for disk drive system. The response is going to be, I may come back to this home assignment when we solve the second order differential equations. This is a typical good response. Time 0.7 seconds, even 0.5 seconds, settle down. There's a slight overshoot here. This excessive value is overshoot, so it is required 0.1. Rs 0.1 over S means that it's a step function for 0.1. Okay. I think that's the end of this course. I don't know whether, is there any questions so far? What we have seen, we have first started with correction of the error, what I have done last week. We corrected that one. Then we have seen sensitivity. We also have seen how could we make nonlinear system linear, okay? And then we have seen the mechanical quantities particularly, and also electrical quantities, stored energy, and also the relationship between electrical and mechanical rotational systems, translational systems we have seen. You can't see me. I understand that. Just a moment. You will be seeing me right now. So we have also seen various mechanical systems, the electrical system, particularly we concentrate on rotary systems or translational motion systems. We have derived electric machine equivalent circuits, and we have seen the performance of the electric machines by looking at this one. Finally, what I'm going to say, let me look at how many of you are in the classroom. We have now 19 students in our classroom. Evet, 18 var. Benimle 19. Şimdi Seyit Hoca da geldi. Onunla 20 oluyor. Bir şey anlatacağım. Ondan sonra sizi Seyit Hoca'ya bırakacağım. I'm going to leave to you. Is this one? Don't leave. I'm going to take a attendance list as well. Oh, I have to clean that one. I don't know whether you can see that one later if you want. Why don't we can open more white papers? Mohammed, yes means you can see it later when you study. Is it recorded already? Tamam. Şimdi siliyorum ben bunu. Evet. Şimdi bir electric machine, torque electromechanical, torque electromechanical versus speed mechanical. Oh no. Alright, Muhammed bir 5 dakika verir size. This is the torque versus speed curve. Okay. When you, for brushless DC motors, these are constant lines like this. Okay. These are torque electromechanical with different voltages. Okay. But torque demand is the one. Assume that it's a lift, for example. So the intersections are the required speed values. Okay. This is torque demand, torque load. Mohammed, we'd better give them 5 minutes break. Okay, so these are your operating points. Intersection between what machine produce. These are steady state operating points. This is not relevant to my course directly, but you should know that torque produced by electric machine should satisfy the load. Tamam mı Muhammed? Okay, I'm going to take an attendance list. Just don't leave. Ali Umut ayrılmış, onu da kaydediyorum. Gitmeyin bir tarafa. Çünkü bu kaydı ben bir göreyim ondan sonra. Evet. Now you can leave. All right. Thank you very much for listening. See you next week. Bye-bye. Seyit, hepsi senin.
We will start the lab in a 5 minute, guys. 5 minute break, then we start the lab, okay?
I'm confused. Is there gonna be a lab today or not?
Yes, there's a lab, just 5 minute break. There's a lab. We will start in 5 minutes, all right? At 11:40. Okay, let's make it. We'll start 11:45. Okay. Okay, guys, let's start our lab. Everyone can see my screen? Yeah, so everyone can see my screen, guys, right? Yeah, okay, let's start it. Okay, the previous lab we have seen like a graphical user interface of the MATLAB. Let's start start with some comments. Let's say you wanna try display a variable in your screen. Let's say temperature equals to, let's say, 60, right? Enter, and then you write display open parentheses. You write your variable inside display. Let's say temperature. Right, when you hit enter, it will display your variable here. You say you temperature equals 60. When you put this temperature inside the display, it will give you like 60, which one you uh, set up to 60, right? Or you can like define it like to display and can add the degree, let's say, right? After the 60, we want to like display a 60 degree, let's say. Will display the degree, but you have to put both of them at the same time. Let's say display, you open parentheses, temperature, and then dot comma. Dot comma means there's another new line of code. Then you check display, open parentheses, and then degree. See, temperature equals 60. Temperature. All right, here we forget an S here, so let's write it here again. Say 60 degree. As you can see, you can write this display on your screen. Also, you can try to plot your imaginary numbers. Let's say z equals 1 plus, let's say, 2j, right? And comma. And then you can say plot. Open your parentheses. The first one is z. You define z, comma, and then exclamation point. Then you can decide which figure will show your z. Like you can use dot or you can use x. Let's first show with dot. It should plot our imaginary number and show it with dots. As you can see here, it will show it. Let's say 1 in a x-axis and in a and in an imaginary number, imaginary axis, it's in 2. You can change it this dot to, let's say we want it to show with the x. You can show it with x2. You see, as you can see, it plotted and show it with the x. When you click it, it will show your x is 2. Let's see, x is 1, y is 2. Also, you can just compass it and write compass, but not with capital. Open parenthesis, just write z in it, hit the enter, and it will show it like this, your compass z. So far so good, guys. Still here. Is it like slow enough or too fast still? It's good. All right. Okay. Okay. Let's say we have a vector and we want to get transpose of it. Let's say a equals to, open your parentheses here, 1 2 3 4, let's say, right? You hit enter. This is your vector, and you want to get define a b vector as a transpose, right? You know, transpose a vector, you get the row and turn it to the column, right? You hit it, it will take your transposes and define it as b. You just add this sign here, and you will get the transpose of this vector. All right. Okay, guys, let's go with the, let's say, imaginary number also. Let's say we define our z as imaginary number, right? 1 plus 2j, right? 2 plus 5j, 6 plus 8j, right? You hit enter. And then you can also take transposes of it. Let's say y equals to z transpose, right? This is your imaginary number transpose. But the transpose of a like z here, it's equal to conjugate transpose. Like in Turkish is eşlenik transpose. If you want to get just transpose of a z as a defined in imaginary number, in a complex number, you can just, let's say, w equals to how you can say z dot and comma, right? We'll just show it like this. The first one like this, when you define it, it will get conjugate transpose, and if you define it like this, it will just get normal transpose of it. All right. Okay, let's go back to transfer function. How we get transfer function of a system? Let's first place our system. We define our system equals to, let's say, transfer function of a system. This TF means transfer function, system means your CSS means your system. Like your system equals to transfer function, which is, let's define our transfer function. Let's say numerator is 1, which is 1 over, and you get your comma, and the second one is your denominator, which is, let's say, we define it 1 1, which is 1s plus 1, right? And then when you just hit the enter, it will give your system. Also, you can plot your step response, or say like step, this one. You'll just write step, open parentheses, and you write your system in it, hit enter, it will give your step response. You see here, it gives you step response of your system. This is amplitude, this is time. Let's close it, let's go on. Also, you can show your system like this, let's say numerator equals to, let's first clear this. Numerator equals to, say 1 4, right? Hit enter. Denominator equals to 1 2 3, let's say. All right, you can define it like this. Your numerator, num is your numerator, den is your denominator. Then you can just write system all transfer function equals to TF, you open parentheses, And here you can define it like this: numerator, comma, denominator. And this will give you your system transfer function here. As you can also show it with time continuous time transfer function, right? So far so good, guys. You understand till here? What's our numerator, denominator, system transfer function? And we plot our step response. Yayın gitti. Everyone see my screen? Is it all good? Screen is got, okay, let's. Now you should be able to see, right? Everyone see my screen? Okay. Last time we did our system transfer function here. Everyone followed till here? We define our numerator, denominator, and then we define our system transfer function. Yeah, all right. Okay, let's continue with, let's say, we have a two transfer function. Let's clear this. Let's say we have a systems, let's say more than one system, and then we will try to add this system together, right? They could be in serial connection or parallel connection, right? Let's start with serious connection, all right? Let's define our num1, all right? You can define it as num1 equals to, open parentheses, let's say it's 10, right? Num2, or let's say for define denominator 1, 2 also. Let's say it's equals to 1, 2, 10. Denominator 1, also numerator 2 and denominator 2 also, we're going to define it. Say this is 5. You can add like dot comma here and then just write another line of code too. Let's do it in that way. And we want a denominator equals to, let's say, but denominator 2. We define our first one. Let's forget that it's 1, 5, let's say. All right. So now in the right side, you see workspace. In workspace, you can see denominator 1, denominator 2, nominator 1, and 2. The code you write here, it will give you workspace. When you click them, you can see here in the value, right? 1, 2, 10, or denominator 1. 1, 2, 10, we define it as here. You can click it and see it also. Let's say we want to add these two systems, right? We have a numerator 1 and denominator 1, numerator 2, denominator 2. We want to add these two systems in serial, all right? In serial. How we do it? We open those bracket, right? You get numerator and denominator, and then you hit equals. After this, you get series, all right? And then you open your parentheses. You just write in num1, comma, denominator 1, right? Comma, num2, comma, denominator 2, right? And then let's say dot comma, and we wanna print our system. You just write print system, right? And then open parentheses. In the parentheses, you should write just numerator and denominator again, right? We had two system, two system 1 and system 2, and then we add these two systems in series together, and we get this is our transfer function, numerator or denominator. All right, this is okay, guys. Till here, how we add series system in together. let's say we have a pair, we want to connect these two systems as a parallel, all right? How we do it, we just do the same as series, but we just write parallel in it, right? Say numerator, or first, don't forget this. What does S mean? This is your second week, the second lecture. S mean your function, your numerator, denominator, you know? Your system. Okay, let's try to add these two together, like then in series. Now we try to add these two in series, right? We just write parallel. That's it. And in the same we did in a series, we just write parallel, and then rest is same. Numerator 1, denominator 1, comma num2 and 2. And then you also try to print this system. We just write print system, open parentheses, and you just write your numerator, comma, denominator. It is your system if you add the two systems in parallel. All right. Okay, let's say we have a closed loop transfer function. How we add the closed loop transfer function? Let's say we have our first parentheses, numerator, comma, denominator. So in here, we have a closed loop transfer function, so which means we have a feedback, right? How we add feedback our system, we just write feedback, all right? Just open your parentheses, the rest is same. Your first denominator and second, first denominator and second nominator and second denominator. And then you define it as a feedback, and then you can print your system again. And then in the inside, numerator, denominator, right? You define it like this, you hit enter, and it will give you transfer function of a closed loop function, right? Which means we have a feedback. You just write feedback in here, and it will give you your transfer function. Okay, let's say now we try to find zeros and poles of a transfer function, right? Here our screen. Our numerator equals to, let's say, 0, 8, 9, 7. Doesn't matter. Let's say our denominator equals to, all right, you define it, or say we define our numerator and denominator, and we want to find zeros and poles of our function. How we do it? Let's define these two, and then first you write z for the zeros, and then you write p for poles, and then k for your gain, all right? And then you hit equals, write transfer function, and you add 2, 0 and poles, right? TF means transfer function, Z and P means 0 and poles. And transfer function to pole, you transfer it, and then you just open your parentheses, numerator, that comma, denominator, all right? And that's it. When you hit enter, it will give your zeros, your pole, and your gain. All right, guys? Okay, let's say We have a partial function. Wanna try to find partial function of our system. Let's define our nominator. It's not so fast, guys, right? Everyone get it? It's okay. Does everyone follows? Yeah. Okay, let's continue. Okay, let's say we have a nominator. You can define it as whatever you want. And your denominator. Define your numerator and denominator. Let's say hit enter. Partial function of a system. You just parenthesis r comma p comma and again your k. Right? You just hit equals residue. If you want to take a partial function, you just write residue. The rest is same, and then open parenthesis numerator comma denominator. Right? Let's say for so that's it for today, guys. Everyone get it? Next week we are gonna start our actual experiments. So you can review this lab. Next week we are gonna start our experiments. So yeah, that's it. Okay, don't leave. Let me take a attendant list. Okay, I got the attendant list. Okay, now you can leave, guys. Have a nice day, guys. See you guys. Have a nice day.